Okay, the chi-square goodness of fit test is a test to see whether whether your data comes from like an expected distribution. Like let's say, just a real quick example: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. One person says the number of customers we get every day is the same. Okay. Uh, We expect 1/7 of our customers to come on Monday, 1/7 to come on Tuesday, 1/7 to come on Wednesday, etc. Okay, but we can compare that to our actual data and use a chi-square goodness of fit test to see whether they really did all come from one day. Like maybe we got 2/9 here, 1/8 here, etc., etc. There's some differences, but maybe the differences are just because of random error. Maybe they're not. Maybe the difference between the data and the expected are because of just random chance. A chi-square test can tell us whether it doesn't seem to be from random chance, whether it's too extraordinary. Okay, so that's the basis of a chi-square goodness of fit test. So a survey company puts out a survey asking people two questions. First, it asks if a person uses public transportation. Second, it asks whether or not the person supports an upcoming environmental protection bill. The data are recorded in a contingency table. The company wants to determine if support for the bill is independent. So this actually sounds like a different chi-square test here. Okay, so they're making some sort of contingency table. Maybe didn't pay too close attention to what the variables are, but there's two variables. There's a category up here, and there's a category down here. Okay, so this is called a chi-squared test for independence. Okay, you're testing to see whether these two categorical, in other words, these two qualitative variables are independent or dependent on one another. That's different than a chi-square goodness of fit test. Okay, so if you're working on a different question, if they're trying to compare two categories and see if they're independent, that's a chi-square test for independence. Okay. So let's check out the next option. A researcher is trying to determine if boys and girls spend a similar amount of time on homework. He surveys a random sample of boys and girls in schools and records the distribution time spent on homework of each gender. He wants to determine the distributions are the same. So really, if you got two columns of numbers and you're trying to determine if they come from the same population or not, that's a chi-square test for, oh, I don't know how to spell this word, homogeneity. Okay, that's when you test to see if two variables come from the same population. And with all these tests, there's different versions of the test where you can expand it. It doesn't necessarily have to be just two variables, but that's just what you commonly see. You know, you got one set of data, you want to see if it's the same as a different set of data. So we got the column of boys, column of girls. We want to see if they come from the same population. That's a chi-square test for homogeneity. Okay, so that's not it. We're supposed to find a chi-square goodness of fit test. A referee wants to make sure the coin he uses for the opening coin toss is fair. He flips the coin 30 times and compares the number of heads and the number of tails. So that sounds like our first example, which is a chi-square goodness of fit test that we said. Okay, instead of Monday, Tuesday, Wednesday, Thursday, Friday, we've got heads and tails. I'm just going to use T for tails. Okay. So the heads column, we have an expected amount, 1/2, and we expect 1/2 to be tails. But then we can actually fill in the data. It might be like 3/8, and this is 5/8. Okay, and then we can run a chi-square test for goodness of fit to see whether it's really a fair-sided coin or whether it's biased in some way. Okay, so anytime you do that, where you compare some actual values to the to expected values, you're probably talking about a chi-square test for goodness of fit.